Host now. Hello.
Yeah, Sachin.
Yeah, already passed to Mr. Jung.
Thank
Yes,
you.
I got it.
Yeah.
Nimesh, how do you want it? You want to have already the main screen up with the introduction of the welding topic and the hosts?
Yeah, that would be good.
Okay, let's see. Share screen 2.
Yeah, fantastic.
That would be the one.
Yes. So we wait for a couple of minutes more. Then you can start off with the introductions, and I'll just welcome everybody.
Correct.
We'll go on mute.
Darren.
Except Graham, of course.
Maybe after an hour or so.
Yeah, right.
Just while people are joining in, another 2 minutes. We just recently, today was the last day at the National Welding Seminar at Chennai in India by the Indian Institute of Welding, and they celebrated 50 years of the branch of inception. And it was a good session. We had a lot of talks from senior scientists from Indira Gandhi Center for Atomic Research and other places. And it was a good 3 days of many interesting topics of discussion, including some 3D printing with metals and also a lot on the nuclear side. So I think all in all, it went well. We had a presentation at Sigma Weld. We did present about the induction heating applications for increasing productivity in chrome molybdenum products, and also something called Sigma Weld accelerated TIG, which is a keyhole TIG process, which allows you to weld square butts at very high speeds. So we did that, and well, it was a good session and learning and exchange. So we're looking forward to another one, which is the branch welding seminar and the Golden Jubilee celebration of the Bombay branch, which is the Mumbai branch now. And it will be held on 11th of February, for which we are really thankful to you, to the Nickel Institute and the Indian Stainless Steel Association for being a part of it. And we look forward to good sessions over there as well. And just as a request to all our visitors, it's good to be a part of the upcoming session on 11th Feb. It's in Bombay, and do register and become a member and do attend the session for a day. It would be really nice. Right, so now I think people will keep joining in. So it's about 5:27. We'll just introduce the WeldTech talks. So this is the 25th edition. It started off in the COVID times as a one-off, and with the support of the Nickel Institute and many others, we've been able to have very good deliberations over the last 24 sessions. And this knowledge sharing continues as each month. And we've had very rich discussions and a lot of very unique talks, and it really helped people, and people have kept coming back to us for more. Each session, we've seen a lot of participation from, now the last one, we had about 36 countries participate, close to about 300, 400 people attended, but about 700 people do end up registering, and then they also get an access to the videos, so it becomes a good session. And without taking more time, I would really pass over to George to introduce the Nickel Institute, and thanking you for the support. And I would request you to also introduce Dr. Graham and Gary Coates.
Okay, thank you very much. You got me on the wrong foot with Gary, but I will definitely do that. No, so Nimesh, everybody, good evening to all of you, and a very special thank you to the IIW Mumbai branch for having us on today's webinar. My name is Jörg Schweitzer, and I'm the Market Development Manager for Southeast Asia in the Nickel Institute. This webinar is also supported by the International Molybdenum Association. I would appreciate if you would allow me to quickly introduce the Nickel Institute and IMOA to you. As you all might be aware, nickel is a key element in more than 75% of all stainless steel produced. It delivers outstanding physical as well as mechanical properties. That's why stainless steel is such an attractive, easy to use and long-lasting solution. We, the Nickel Institute, are a global non-profit organization of the leading primary nickel producers. Our mission is to promote and support the proper use of nickel in the appropriate application. Our headquarters is in Toronto, Canada. We have an office in Washington, and in Durham, South Carolina, USA, is our Science and Research Center. The European Center of Excellence of the Nickel Institute sits in Brussels. There are 2 more incorporated offices, one in China and one in Japan. Then we have 2 representative offices. These are located in Australia and in Singapore, where I'm sitting. This is an overview of our membership that funds our organization. IMOA is like the Nickel Institute, a non-profit organization. It represents the majority of the molybdenum industry globally, and it promotes the properties and sustainable benefits of molybdenum in a wide range of modern-day applications. Molybdenum is a key alloying element to provide improved corrosion resistance. So we have as well tonight Gary Coates. Sorry, Gary, I don't have a slide on you, but Gary, most of you know him from previous webinars. He is our technical manager in the Nickel Institute. He sits in Toronto. He actually provides as well webinar technical help. He is actually, when it comes to technical questions, our brain within the Institute. So that's for Gary. Then Graham. Graham is the Nickel Institute technical consultant, and he's working for the Nickel Institute for over 8 years. He's a corrosion and materials consultant since 1985 in the UK and Australia. Furthermore, he is a technical specialist for the Australian Stainless Steel Development Association for more than 20 years. And importantly, he is active in ASTM and Australian standards development, including stainless steel pickling. And that's very interesting, AS/NZ standard for welding stainless steel. With that, I would like to hand over to you, Graham. You all enjoy. Thanks.
Okay, let's see if I can get the system to work. No, it
I
says
have stopped sharing.
right.
Right. George, you may want to just click and make Graham the host. You can go on to the participants. Click.
Participants, yes, correct.
In the panelists, you will see Dr. Graham.
More, yes, correct. Make
Make
host,
Yes.
change host.
Done.
It's done.
Yeah.
Should be over to you, Graham.
Yeah, okay, just give me a sec.
No problem.
Okay. Everybody see that?
Yes.
Yes, we can.
Okay, thank you very much for the introduction. This is the slide that Jörg showed, except there's a slight difference. There's 2 little examples of galvanic corrosion. Neither of them are welded. Here we've got a stainless steel screw in a nice piece of aluminium, It's been painted on the aluminium, but the painting wasn't terribly good around the edges, and so it's corroded like crazy. And the other one, we've got a piece of stainless steel flange and a stainless steel bolt, and somebody has just put a piece of carbon steel there, and so we've got galvanic corrosion. So that's what we're talking about. We're talking about dissimilar metal corrosion. Where are we? How do I go? How do I advance? Something's gone wrong.
It's okay. You just got to click next.
Yeah, right. Okay.
There are two small arrows at the bottom as well, so you can use them.
Right, I can see it. Yes. Okay, thanks. Across to the left. This is basically a summary of what I'm going to talk about, so I'm not going to go into that in detail. This is 4 steps of corrosion. Okay, so corrosion, everybody thinks that it's basically the piece of metal falls apart and releases positive ions, but it also releases electrons into the metal, because obviously you can't go separating charges. And so then the electrons flow from there to the cathode. Now that may be of metal, it may be all sorts of things, but yep, does that. The third step is those electrons reacting at that point. If you're talking about dissimilar metal corrosion, then you may wind up with precipitating a metal if it's in a solution of ions, or if you're talking about a piece of stainless steel, then you may wind up with the electrons just forming hydroxides with the water or the oxygen. And the final bit, and the bit that's absolutely critical, is that you've got to have an electrolyte. And the electrolyte has both the anode and the cathode in it. Otherwise, it doesn't work. And you get ions flowing in the solution. So you need all 4 of those, okay? If you stop any one of them, then the corrosion just stops dead. You can fix it up by changing the materials or changing the environment. And if you're talking about dissimilar metal corrosion, then you've actually got to make sure that, well, you don't need to make sure, but you won't get an acceleration effect unless one of the metals that's in the pair will corrode or be close to corroding. Otherwise, it just doesn't matter. So if you're putting, say, 304 and 316 together and they're in a solution where neither will corrode, then you'll get absolutely no effect. If you're talking about submerged or buried environments, then you can actually apply an external current. That's nothing to do with dissimilar metals. That's just applying a current. And then you can get cathodic protection, which will decrease the attack, or you can have straight currents. So I'm going to, a bit later on, talk about straight currents and how they're different from dissimilar metals. But basically, corrosion is an electrical system, and so you can fiddle with it by applying currents. This obviously is going to be very familiar to people. This is straight out of ASTM G82, and the references here, you've got various metals and they have various potentials. Against saturated calomel electrode, that's a convenient laboratory equipment, but you can use silver chloride, copper sulfate, or if you're doing research work, and very rarely is it done this way, you could use a hydrogen or reference electrode. These things go from very, very dissolving things down the bottom, right up to graphite, where at the top corner there, you get no corrosion, basically. This chart is for flowing seawater at about 30 degrees C, and note, there's little black bits on, say, 316, or a white bit open. And that's basically the 2 states that it can occur in. If it's white, that's where you want it to be. It's not corroding. If it does break down and start corroding, then the potential pulls back down there. And that's the same thing that's happened for 316, for austenitics with 18, so a 304, down to a ferritic at about 16, or a martensitic at 14. All of the stainless steels have this dual arrangement, but because you don't want your stainless steel to corrode, then it should be in the zone where you've actually got the open square there. There's an FAQ on the ASDA website, which has got much the same sort of thing. This is a similar thing, but rather less cluttered, just to show you a little more clearly. And it's for seawater at 10 degrees C. What I'd like to point out to you, though, is this group of alloys: nickel, aluminium, bronze, 90-10 copper, nickel, alloy, brass, copper, even austenitic castings, are all at about the same potential. So if you connect them together, then it's really not going to be a defect in terms of dissimilar metals. There are other things outside, though. This is from Roger Francis's stuff, published by Francis and Byrne. And this is looking at a super duplex stainless steel in seawater. So normal seawater, it sits at about that sort of potential. You've got a biofilm on the surface. You've got a bit of oxygen there. If you heat the thing up, so it's 20 or 30 or so degrees more, then no biofilm, no potentiation of the oxygen, and so it drops to there. You can deliberately deaerate it, pull it down to there, or if you completely deaerate it, down to that point there. If you want to go the other way, then chlorinate it. Put in 0.5 to 1. That's quite a bit of 1 milligram per litre chlorine continuously is quite a bit, but still. What I'm saying is that not only is it a matter of the material itself, but the environment that it's in. And I've just been talking about that: oxidizers, chlorine and oxygen, the microbes, and the temperature, because the temperature does things for the microbes. This is in freshwater, moderately hard water, 25 degrees C. And it's a bit different, but here, look, stainless steel, copper, 90-10, alloy brass, dezincification resistance, so it's got a little bit of arsenic in it, gunmetal, silver solder, all about the same potential. So in moderately hard water at about 25 C, those won't corrode against each other. Low galvanic. This is an example, stadium in Detroit. We've got copper here, we've got a bit of brass, oh no, there's no brass there, and this is stainless steel, no corrosion. This is in a hospital in Scotland, brass, stainless, copper, stainless steel. They're all compatible because of their fresh water. This is a freshwater series, and the reason I'm putting this one up is because the graph is reversed. So here we've got the high potential or low potentials that side and high this side, and still we've got the things that are going to corrode right down this end and the things that aren't going to corrode down the far end, and you've still got the sort of S shape in it as well. Oops, not quite what I meant to do. And again, you've got this batch in the middle where the potentials are all about the same, and so if you put any of those together, then they're not going to corrode, not galvanically. Sorry, I'm clicking the wrong buttons. But you can also get these sorts of charts in various other things. So here we've got tap water, distilled water and seawater in the middle. We've got hydrochloric acid over here, and we've got nitric acid over here. Why you do that? Well, because you've got very, very strongly reducing hydrochloric acid, very, very strongly oxidizing nitric, and these are the sorts of potentials that you will get on various metals. This is basically putting a line rather than the names of all the various elements. Real world, things are a bit different. And I just thought I'd put this in just to give you an indication. Here we're talking about a stainless steel. Here we're talking mild steel and concrete, and they're about the same potential, which is the reason why stainless steel and carbon steel reinforcement can be connected inside concrete. It's one of the questions that keeps coming up, despite the fact that it's been absolutely proven for a long time, 20, 30 years, that you have no problems with putting those two together if they're inside concrete, and it's simply because the pH is way down. Okay, so let's look at some real examples. Here is a bit of a stainless steel tank, and here is a copper pipe coming into it. And as you can see, the copper pipe has got quite a significant bit of corrosion. Why? Because there's an enormous area of stainless steel, and so it overwhelms this. So it's not just the potential, but it's also the area of relative area of the two. Here we've got, it looks beautiful, doesn't it? But it's all rust. And it was a tank, a bolted tank, and they started getting leaks. And so they put in some a piece of stainless steel inside to bolt things up to it. What they didn't do was isolate it from the tank, because it's a painted tank. And at the cut edges, there was an exposed amount of steel, and so it corroded. And so it very rapidly got this sort of appearance. And they wondered what on earth it was. It was pretty straightforward, but they just had to change the way they put it together. And when I say treated water, it's basically the water that's used for flushing toilet systems. Okay, let's look at other examples. And I'm not talking yet about welding things. I'm talking about actually putting things together. Here we've got a door, two metals, aluminium here, stainless steel here. And as you can see, there's a bit at this line here, a bit of white. So there's a bit of corrosion going on the aluminium, just because of the galvanic thing. And you'd think, well, okay, it's going to get wet sometimes, so there'll be a problem. But it's actually not too bad, because the design, it's vertical, so the water runs off. It's hopefully just going to be rainwater, and except down beside the sea, there won't be an issue, but still. And the inherent passivity of the stainless steel, and I'll talk about this a bit later in terms of numbers, but there isn't an awfully good effect as a cathode, actually to use the electrons up by the stainless steel. And quite apart from that, it's fairly obvious that there would be anodizing to actually prevent the corrosion of the aluminium as well. Yeah, this is one of those lovely little examples. Somebody thought that they'd, this is marine, obviously, and they had problems and they had to put some sort of system in to reinforce. So they thought, well, we'll put some stainless steel bolts and hold it together. And they put that through and painted the thing, and very rapidly they found this had happened. So it's not quite obvious there just how it was put together and that happened, but basically if you're painting something and you put a bolt through it and you tighten it up, then all of a sudden you've lost absolutely any insulation you may have had because you've damaged it. Alternatively, what they could have done was weld this whole thing in and then paint it. But it's not terribly easy to do a full-scale multi-system paint in this sort of environment where you're getting lots of splashing. So while this wasn't a great idea, the other idea of actually welding the thing up and painting it to keep the materials from corroding, and quite apart from the fact that you're not even then looking at, if you're just using ordinary bolts, you're not looking at galvanic effects, you've still got a problem trying to do it. This is a simple galvanic thing. It's one of the things that I have frequently shown. This is a flange in super duplex, and here is an area where you've got crevice corrosion. Actually, it's not only crevice, you've also got a galvanic effect because the gasket that they used had significant levels of carbon in it. And so you've got carbon right up the far corner and stainless steel well down from it. And so even the super duplex suffered corrosion. This is rather more mundane. This is a piece of stainless steel up there. Here is an aluminium frame supporting it. And somebody said, we can't do that because we've got a galvanic problem. So they put a gasket in there, which was a bit of rubber. And it wasn't done terribly well and things dribbled past. And so what you can see is that you've got a tack of the aluminium underneath the paint and the paint's blistering off. So it's driven corrosion down here and you wonder what's going to happen. Well, that's what happened. The whole thing fell off. Now, how could they have fixed that? Well, they could have used a proper insulating material, but in fact, they should have thought perhaps and put stainless steel on this support. This is a little example of, says he, desperately trying to get the thing to work. There we go. Yep. This is an example. We've got a small bit of aluminium in a large piece of stainless steel, comparing that to a piece where we've got the stainless steel in a large aluminium anode. And if you look, you'll see that around the small bit of aluminium, we're getting all sorts of corrosion forming, whereas around the stainless steel, you're getting no corrosion forming at all, basically, because it's very small. This is a classic example of a small boat. Here is a bit of painted aluminium and nice stainless steel bolt or screws holding a hinge in it. It's just a cover. And what you can see is that there's got exactly the same as with the handrail, corrosion of the aluminium, blowing the paint off, and away it goes. How do you get around that? Well, you could paint the stainless steel and paint the aluminium. Both would work. Rather difficult to actually avoid having the connection underneath. And this is the other example I showed on the front page. Here, again, you really are going to have a problem with this sort of fitting. Yes, you could paint the whole thing and you'd have to paint all over the stainless steel, or you could weld the whole thing and then, yes, okay, if you're welding aluminium to aluminium, that's fine. If you're welding stainless steel to aluminium, bit interesting, but you'd need to have some sort of coating to stop the thing. And yes, that's basically what I've said. You can put in insulation. Obviously, here we've got steel, here we've got aluminium, and washers there, keeping them off. And this is the example on the front where no insulation at all, and it's just a standard 316 fastener. So let's look at a few examples. Carbon in a porous gasket on a stainless steel flange. Well, you've already seen that with the super duplex. Stainless steel and aluminium, think about the door handle. Yep, it may be okay because stainless steel is not a terribly good cathode, and the aluminium, it's not, well, it's well different, but it may well have an anodized layer on it. Stainless steel and galvanized steel, the severity there is very much going to depend on the environment, because if it's a strongly corrosive environment, then yes, this galvanized steel will suffer. But if it's reasonably inert, then you probably won't get terribly much. Mind you, both of these need a reasonable amount of rainfall on them in order that they're not going to actually corrode full stop. Stainless steel and carbon steel, well, yes, every time you get that, we have all sorts of strife. Galvanizing in carbon steel, let's get away from stainless for a moment. It's okay for roofing, old galvanized. In Victoria, they call it, or in Australia, they call it galvanized iron when they actually mean galvanizing on carbon steel. But if you look at the old system, they used to have galvanized pipes going into hot water tanks. And in some waters, some bicarbonate waters, if you got the temperature over about 65, there was a polarity reversal. So, and the galvanizing didn't dissolve, the carbon steel dissolved. So every now and then you need to think a bit carefully about what's going on. Carbon and aluminium, well, yes, they're far apart. Do you ever get a problem? Well, yes, I've seen a couple. One was an aluminium tray truck used for carting carbon black, and they spilled bits of it. They got some salty water on it, and they wound up with holes in their truck. And carbon black loading in insulating washers for roofing screws, tech screws they're called here. If you get more than about 30% carbon, then you can get continuously conducting electrical networks, and away it'll go. In each of these things, the first in the pair is noble or cathodic, and it's not going to corrode. So I've talked about what is corrosion. what potential ranges there are there and how they can change, and a couple of examples of galvanic attack. If people want to ask, no, let's save the questions till the end. Okay, so what drives galvanic corrosion?
We can request the people, if they have any questions, to post it in the Q&A session section at the bottom, so that Graham can take it up at the end. Dr. Graham.
Okay, fine, thank you.
Thanks.
Potential separation. Less than 200 millivolts is often going to be okay. Very rare if you've only got 100 millivolts separate for it to actually be a problem. It can happen if you've got a very tiny anode and a very big cathode, but it's pretty rare. And that's what this example is about. The thing is that stainless steel really isn't a terribly good cathode. A fairly low passive current density, you're talking about 10 nanoamps per centimetre squared, nano as in 10 to the minus 9. And both metals are going to be at the same potential if they're corroding because they pull in together. But the Tafel slope for stainless steel, 120 millivolts or so, and you need at least a microamp per centimetre squared to corrode. And I'm sorry, I'm getting awfully electrochemical and technical, but basically I'm just trying to point out to you quite strongly that stainless steel is not a good cathode, and that's why. Physical distance and geometry, so how far apart they are can be quite important, but talking about pipes, well, it's going to depend on the diameter of the pipe and the conductivity of the fluid. So in seawater, you've got about 10 diameters for the 50 milliseconds per millisiemens per centimetre versus about 3 diameters for freshwater. Keep that in mind when you're putting in a separation or you're putting in a sleeve down a tube on a heat exchanger, that it depends very much on what the conductivity of the material is, how far down you've got to shield, and the corrosivity or the oxidizing capacity of the solution. If you've got really high levels of chlorine or peroxide or ozone and so on, then you can push your stainless steel right up into a transpassive region and it'll start corroding just by itself. But that's pretty rare, and it's nothing to do with galvanic corrosion. It's just simply corrosion. And microgalvanic effects. These are things like precipitates from poor heat treatment. So this is carbides or sigma or so on from welding usually or heat treatment, or dezinkification of the two-phase brasses. And I'll talk about that in a few minutes. Okay, this is to give you an indication of how far apart you have to have things before you can say, we don't have to worry about what's going to happen and what the environment is. This is looking at zinc protection across a carbon steel flat surface because it's a relatively easy thing to measure. So surprising how far things will go, but still. So 100% relative humidity, you get very little protection, you get very little conductivity through the film that's on the surface. If you're going to spray it with deionized water cyclically, then nothing's going to build up. It's going to wash clean. If you're putting tap water continuously on it, then yeah, the tap water is going to be a bit more conductive, depends where you are, but it's going to spread a bit further. If you're looking about urban atmospheric, this is basically going to depend, pardon me, whether you're down beside the sea or whether you're out in the middle of the desert or in a standard urban environment. The tap water cyclic spray, well, tap water, it's basically comparing that to that, and there's not a lot of difference in those two, but you can get building up concentration, and so you get a bit of conductivity across the surface. Sodium sulfate spray, seawater spray, 5%, or continuous immersion. So you will get, this is with deionized water, so it's not a great conductor, but it's still something that means that you could go 5 centimeters or so out. Now, what does that mean? It means that all the electrochemistry is happening if you've got a point, if you've got a fastener sitting there or something sitting there that's going to cause galvanic corrosion, then the area around it within the circle with, in this case, 5 millimeters, sorry, diameter around it is also going to contribute. And if you had seawater, then you'd go out even further. So the effect is, damn it, you're effectively measuring resistance of the thin surface film. This is perhaps a more interesting thing, looking about straight galvanic corrosion. And we're looking at hot dip galvanized steel sitting there, there, and there, the light blues, and the hot dip galvanized connected to a bit of stainless steel. 6 times the area of stainless steel to the galvanized, so it's a bad ratio. And then we're looking at corrosion rates in micrometers there, micrometers per annum. Okay, in the urban atmosphere, not much and not much difference. Near a steel mill, so you've got sulfur dioxide and things like that. Coastal areas where you've got salt, sea salt and so on. But it goes really through the roof when you talk about what happens with splashing. So you're getting splashing on the surface, concentrating up, and away it goes. And yeah, that's what I just said. So this comes out of a Euro Inox publication. And there's the reference table at the end. And it's basically saying the definition of galvanic corrosion. You've got an anode, you've got a cathode, and you've got an electrolyte sitting on top. So it doesn't talk about the 4 steps, but basically the bit down the bottom that's critical is that one of these has actually got to be able to corrode in the electrolyte that's there. Otherwise, either got to corrode or be close to corroding. Otherwise, there won't be any galvanic acceleration. And that's what I just said there. I've said it before, but I'll say it again. If the cathode is going to be stainless steel, then it's not terribly efficient. And so it may not be really bad. Look, I know people will say, hang on a minute, what about we put a carbon steel bolt in or we put that washer in? Yeah, sure. It's very visible. It's not so visible if it's aluminium. It's not so visible if it's galvanizing. And it's still there, but it may not be a serious effect. And the galvanic area is very important. This is back to looking at Davy with his putting copper onto boats to get rid of woodworm. Yeah, wooden boats. And he found that the steel corroded very rapidly, and that was a problem. So then he started using the other way around, and it worked quite well, except that he didn't have enough copper there. And if the area of the anode is more than about 10 times the cathode area, hey, galvanic corrosion is not all that likely. And it really doesn't matter all that much what the potential difference is. That clearly, that's not completely unlikely, but at the reasonable levels of difference, the 10 times is pretty good. If you're the other way around, then if the anode is 1/10 of the area of the cathode, then you're likely to be in trouble at really quite low potential differences. So in fasteners, this is a little model. We've got fastener active, fastener noble, and what's going to happen? Oh, it's going to corrode like that, it's going to corrode like that, and it's going to fall out. That's not good, okay? So basically what this is saying, that fasteners should always be down the bottom, more noble. And then, yeah, you can get some corrosion either side, but that's not going to be really a problem. Except that if you weren't too careful about putting it in and it doesn't fit too well, then you can wind up corroding away the active material next to it, and you get a loose bolt, and eventually a loose bolt falls out. This is classic examples. The one on the right is the Petronas Towers before they realized that they'd made a mistake and put up some galvanized well, no, actually, I think they were just electroplated zinc bolts. But David Jenkinson took this picture of the Nickel Institute, and he came back a few years later, and hey, they'd replaced it with stainless steel. Here we've got, again, stainless steel. God knows what this is. It may have been zinc electroplate. Over here, we've got stainless steel, and then again, zinc electroplate. And there's a bit of corrosion around there and there, but this is the bit that I'm really wanting to talk about. So bolts, watters, nuts, they've got to be more noble than the bulk material. If you're using stainless steel on stainless steel, then you'd use the same or higher. But remember, again, PRE, if that gives you the raw numbers, but if you're looking at stainless steels and the environment isn't too bad, then it's not a terribly good cathode. Next slide's got some tables of acceptable metal combinations. And if you're going to have to join dissimilar metals, then use some insulation. Now, clearly, if you're welding something together, you can't put insulation in there, just not possible. So we'll talk about what we do then in a moment. If you're using insulation and it's going to be permanently damp, then you need to make quite sure that the insulation doesn't absorb water. And there are some nylons that do absorb quite a bit of water. There are others that do, other materials that do as well. So you just need to check that. And then if you're going to insulate, you do insulation between in that direction, but you also sleeve it down here. Now you can either do it with top hat washers or just put a sleeve around that. Some diagrams leave out the sleeving around the bolt, and then you've got the probability of getting connection between and then down and around, and you lose your insulation. Now, this is, I'm sorry, it's out of an atmospheric corrosion book, published back in God knows when, 70s. And looking at zinc against zinc, it's fine. Zinc against stainless steel, yes, not great. Aluminium against stainless steel, B, a bit of an effect. Ferritic against these, that should be okay. Over here, we're talking about A, D, and E. They're a little bit complicated there because when we're talking about the D number, sorry, I'm just moving this blessed thing out of the way. Talking about plated materials, then you can get consumption of the plating on the surface, and the corrosion of the fastener can be, if you've got an E anywhere in that, then the corrosion of the fastener can be made quite rapid. So we're talking about aluminium. So this is the fastener, that's the other material. And look, you'll see diagrams like this everywhere, probably rather clearer. Okay, back to the electrolytes. This is how you control galvanic corrosion. You make sure it's dry, or you exclude the moisture somehow or other. You make sure that you don't actually get moisture going between the two. You can put a coating, and it's shown here that you put the coating on the cathode. Well, now, why would you do that? Why wouldn't you stop the corrosion by putting something on the anode? Well, that's easy. If you get a small hole in the coating, then all of the corrosion concentrates on that point. And so you always coat the cathode. I can remember looking at a submarine where there was some instances of coating, and somebody who really didn't know about corrosion was saying, okay, we'll coat over there, and point out to him that no, wouldn't work. Paint the cathode, any small defects will not be able to deliver much current. And insulation, if you've got insulation like this, then you also must not absorb moisture, but I've said that before. Okay, so let's get serious about looking at welding and corrosion, or galvanic corrosion. Here we've got a lovely piece of stainless steel down the bottom, and here we've got a piece of painted carbon steel up the top. And we've got corrosion around there and draining down there, and that's not good. What happened? Well, the first thing that happened was that they didn't clean all of the muck off the weld, so that the paint just fell off. But typically, you need perhaps 20 millimeters. Remember that diagram I showed, how far you can spread, how far you can throw the effect? It works both ways. If you're trying to protect, it's good. If you're worried about corrosion, so if you're worried about this acting as the cathode and there's the anode and there's no paint on it, then you have to go a further distance away, and greater than 20 millimeters, maybe up to 50 millimeters, just depends how corrosive the environment is. You need to make sure you've cleaned the heat tint off and clean off all the muck from the weld, and do it mechanically, preferably, because if you don't, then if you're doing it chemically, you wind up just etching the carbon steel as well. And then you paint it, but you do not, under any circumstance, use an active paint. You don't go using zinc rich, because you put that onto the stainless steel, and if there's any defects in the coating, this, mind you, zinc rich would be a primer, of course. If you do that, then you wind up with all sorts of corrosion between the zinc, which is right up one end of the galvanic series, and the stainless steel, which is halfway up. And this is an example of that. Here we've got a stainless steel pipe. Here we've got a support, which is carbon steel, painted carbon steel. And so you put a coating around there. But I'm emphasizing no active primer. And the width of the stripe is going to depend on the environment, how conductive any film might be. So remember the diagram further. If you're down beside the seaside, then you have to go further. If you're directly one above the other, so you can get water running down over it, then you've probably got to go a bit further. But if you're talking about something above it, then it may not be quite so bad. And you'd have similar protection of carbon steel brackets if you're talking about a vessel where you had doubler plates on the outside to go to your carbon steel supports. Okay, atmospheric galvanic currents flow through surface moisture films, and they're bad near the sea. Fertilizer is perhaps a problem if you're talking about being out on farms, or if you're in the Middle East and you've got lots and lots of salt blowing around on the sand and it sticks, and that can be a real problem. If you're talking about immersed things, then seawater is going to allow wider collection, basically because it's more conductive. And if you're talking about fresh water, well, Australians, the water goes from 10 milligrams to 150 milligrams in most of the places, although Adelaide tends to go a bit worse. And it's really quite common to use coated ductile iron castings in potable water valves with a stainless steel overlay for the steel surface, because you don't really want to go closing down onto a coating. Okay, now you look at that and you say, well, hang on a minute. Now you're coating the actual thing that you're protecting. And yeah, it's true. But you do that and you then put the overlay, or you put this paint onto the stainless steel surface as well, so that you have to have less of a throw through the water. And remember, we're talking about potable water. We're talking about reasonably low conductivity. Yes, and it works reasonably well. Every now and then people I've actually gone and looked at a water supply system where they'd used uncoated castings, and they wondered why they were getting all sorts of rust in their water supply. Really mad. Normally you don't coat the anode, but in this case, yes, you do, but you've also coated the cathode, and yeah, that's basically it. Okay, let's look just at the bit where stray currents are a problem. Here we've got a sensor, which was actually immersed in a sewer pit because they wanted to actually measure whether they were going to have an issue and what their dosing had to be. When I pulled it out, this sleeve there was up back here, and I'm sorry, when I took the picture I moved it. So that line there is simply, oh sorry, here the thing's been polished round and round, and the pits on it are extended along the polish lines. That's not so surprising. Down here, that's the crevice where this actually sealed, because that's a tapered fit there, and that's just the flare. Okay. How do we know it was actually galvanic? Well, because it was, sorry, straight current, not galvanic, because it was very quick. This is the end of this pipe. This was a plate that was on the end. Around here is actually the end grain attack of the end of that tube, because it's fairly close to the earth stainless steel gate. Here, there was a label, so there was no corrosion under that, but this is the end plate sealing the end of that pipe. And as you can see, it's corroded away there. And you can see this is just basically the surface has been etched away, but not through the piece of paper. Quite amazing. And I know that was the problem, because the people who supplied this thing paid up for a brand new one, which was really good. It was 30 or 40 grand. These are the mathematics, straight currents. If you're talking about aluminium, 1 milliamp per centimetre squared, you get this number of millimetres per year. If you're talking about copper, you get about that, iron about that, and zinc about that. So straight currents can make things corrode very rapidly. And they're reasonably easy to pick that it is straight current, but the cause of it may be quite difficult. It may be that there's problems with earthing of the electrical systems after faults in a building, or it may be that somebody else has got some cathodic protection and it's got done wrong, but that usually is reasonably well controlled. As I say, leaks in supply wiring, bad earth. One of the classic examples I saw was a copper pipe carrying the firewater around the building. It was loose wrapped because it should have been okay. But the earth of the building was a single banged in bit of pipe into sand. And so it really didn't do anything. Okay, how do you model galvanic corrosion? Well, up until fairly recently, people looked at a reasonably wide range of material couples and surface treatments and looked at immersed potentials, and they gave potential tables, material tables. It was a mill standard. It was applied in aircraft and all sorts of things where there were lots and lots of different treatments, and some of them were quite complicated. That revision D, which is now in use, it's only been out for a little while, they used laboratory tests in sodium chloride solutions to sweep the potential, and that is a laboratory test. You basically start from the cathodic side, so it's not going to corrode, and you sweep through and measure the potentials. And you can actually then do electrochemical calculations and work out what's going to happen. And you can then look at a whole series of treatments. And the next thing is a bit complicated. This is a slide which has got all these materials in it. And the bits that are important are the bits where you've actually got connections here and here. Now, why am I doing that? Because those are the points where the intersection of the line of the, where are we? Titanium versus the aluminium comes here. So this is anodic, dissolving, cathodic, protecting. And compare that with looking at stainless steel, this is the blue one, with the aluminium, or the aluminium with treatment. And you get about 10% of the corrosion rate with the aluminium titanium compared to aluminium stainless steel. So that means you can actually look at it and say, well, okay, this treatment is going to be 10% better, or hopefully even better there. And look, current densities, amps per meter squared, going down to really tiny, but up to enormous. This is basically electrochemistry, and that's all it is. It works every time because it's basically measuring what is happening there. All you've got to do is set it up, make some sums or make some assumptions about whether a 3.5% sodium chloride solution is going to be a reasonable comparison to what it is. And since a lot of the work with aircraft and so on is related to seawater, near sea, then that's basically what works. So you do have to do some sums on anode cathode ratios, but yes, you can do that. Okay, I'll hang off. We've got only a few more minutes left. A few more examples. Area effects, controlling galvanic, and stray current is not galvanic corrosion. Stray current is ferocious, really ferocious. You have petrol tanks in a petrol station and they're painted carbon steel and they have electrical faults, and you can have holes through them within 6 weeks, easy. Okay, this is urban atmospheres, 1-to-1 area ratio. This is the corroding metal, so this is presumably going to be your fastener, and here's your coupled metal, and you're looking at stainless steel. That's the thing I'm interested in, obviously. And put it with magnesium, and that's a bad thing for magnesium. Stainless steel to stainless steel is okay. Tin to stainless steel is okay. And weathering steel is okay, because we're looking at an urban atmosphere, okay? If you're looking in a marine atmosphere, so there's lots of chlorides around, and again, magnesium, yes, weathering steel, not so hot, but that's partly because weathering steel doesn't like chlorides. Tin, yeah, that's now back being okay because the corrosion's gone up. Lead, bit doubtful. Nickel, a little doubtful, which is an interesting statement. But this is useful for a first past the post. And then you look at your area ratios, and then you look at the actual environment. How bad is the marine atmosphere? But this is in atmospheres, it's not submerged. So what about micro galvanic effects in local chemistry? This is ferrite and austenites. Yes, if the material is in an aggressive environment, then you can well get ferrite dissolving. There is a slight potential difference between them. It's not commonly a problem. And hey, you know why it's not a problem? And how I know it, because people use duplex stainless steels all the time, and there is very rarely problems in the galvanic effect. Intermetallic phases in high alloy stainless worlds, de-alloying with denickelfication, or the plug or general dezincification if you've got people who haven't put the arsenic in, or they haven't heat treated it. And the zinc aluminum galvalume, the zinc aluminium alloys where the zinc corrodes, but it's retained by the aluminium. So that works. And these work basically for roof. This is Australia, that's the States. And iron and aluminium. Well, that's bad news, but it's nothing to do with welding. There was a rust dot problem there. There was rogue iron in some out of a major supplier. This is a piece of buried cast iron pipe, and it basically corroded. There's a fairly solid potential difference between the cast iron and the carbon, and it's corroded out. It looked quite good until you sandblasted it, and then it looked like this. It was just holes, and that's the front porch of my old house. Tramline sensitization, you do some welds. This is a spiral welded thing, and it's fine there because it was looked after. This is a rather rapidly done weld in some 316, and they overcooked it, and so you got carbide precipitation there. Why am I talking about this here? Because this is an area where you get chromium carbides formed, and they form like that. If they're just scattered along like that, then they're okay, because the area around there is lower in chromium, and so it's likely to corrode. There's a differential there. And if they're contacting like that, then you wind up with carbide intergranular corrosion. The next slide shows you what it actually looks like if you go in and start looking at the chromium content either side of a grain boundary. And here we've got sort of 18, 19%. And down here, we're down to what, 13%? Okay, it's still stainless steel, inverted commas, but it's way, way down. And so either side of the grain boundary, you've got lower chromium, and so you've got a potential difference. And yes, partly it's the fact that the carbide itself isn't terribly stable, but you've also got a potential difference there. And that's 0.2 micrometer width there, so it's very narrow. Oh yeah, 10.5% is the limit for stainless steel, but 12, the corrosion professionals tend to say 12% is the number you'd think of. Corrosion resistance of this. This is a piece of 316. It was a piece that was used as a heater in some impure phosphoric acid. And you can see very bad corrosion here. This is the sort of 0.5 micrometer corrosion guideline, pitted all over the place. Where it isn't pitted is along this weld. Why? Because the weld is over-alloyed, and that's over-alloyed so that you don't worry about losing chromium and getting a different potential. And basically, you're trying to make sure that the smallest thing there has got the highest potential and therefore is the most resistant to corrosion. And yes, I can see some pits along the bottom here, but that's a crevice basically at the toe of the weld. This is a piece of duplex which was in a very complicated, well, a fairly aggressive environment. The distance across there is about 30 millimeters, but as you can see, the weld has actually been attacked much more severely than the gross metal out here. My understanding from looking at the data was that they basically under-alloyed the filler. They had the wrong filler in there. It's possible that they lost nitrogen, that they didn't have any nitrogen coming in, but I was not able to verify that. Certainly the filler looked to be wrong. The other thing is that here we've got a nice oriented microstructure. Here we've got a spiky sort of microstructure, which is actually going to be more susceptible to corrosion. Sometimes galvanic corrosion can actually be useful. Seawater pumps often have austenitic cast iron body, and I resist on, which is anodic to the 316 internals, and so protects them, especially from crevice corrosion. And you think, wow, that's a problem. We've got corrosion of the body. Yeah, but look at the area of the body, and quite a bit of corrosion current can go without giving you significant corrosion. It's also used in smaller pumps, which have bronze bodies and stainless steel shafts. And you definitely want to protect the shaft, but the body, again, large amount of material. Galvanized zinc aluminium or zinc galvanizing on roofs. Batteries, that's a classic of use of galvanic effects, provided you make sure they're put together properly and they don't have nasty little fires and so on, but still. The Corrosion Association in Australia has got a clock that they run during their conference. They use magnesium and copper in salty water and start it at the beginning and stop it at the end. And any anodic sacrificial coating is also useful too. How can you measure galvanic effects? Well, you can just use a voltmeter, high impedance voltmeter, please, or you can measure the currents with a zero resistance ammeter, or you can put a coupling resistor in with a sensitive microvolt digital voltmeter, and those are fairly easy to get these days. Mind you, they cost a few dollars, but still. You can measure it with wire on bolt things, which is what the ISO people do. They use that for things like wire, aluminium wire, and so on. It's preferentially collects contaminants along the wire in the crevice because it's wound on a thread. And so it gives a fairly conservative estimate. Or you can go away and do Nernst calculations and pretend you're an electrochemist. Here's a bundle of references. This galvanic corrosion, and it's not specifically about welding. It's mainly about galvanic corrosion, but Roger Francis, it's a nice ebook. Sorry, AMPP, please. We've got, ASDA's got a dissimilar metal things. There's an Australian standard which was written by an electrochemist who worked for BHP, and it's an absolutely excellent book, but it really, you need to put your brains in gear before you start reading it. The diagrams I showed in here come from this Euro-Inox publication and there's some Nickel Institute publications on fasteners. And look, you're looking at welds. Welds are a disturbed sort of thing. This is the parent metal. This is the really disturbed area in the heat affected zone. And this is the jumbled up weld metal. And you can have microgalvanic effects depending on where you are in relation to the world. If you're looking at high level duplex stainless steels, then if you cool them down too fast, you get too much ferrite. If you cool them down too slowly, you wind up with all sorts of intermetallic phases and you get corrosion, and that's just right. This bit is the bit where you can get all sorts of galvanic effects, and I'm talking sigma phase and so on up there. This is an example of what happens if you have bits of pipe and you have people welding them improperly, and you get weld repairs, and then you put the things in a test solution, which is a G48 test, ferric chloride, and the ones that had been weld repaired looked like this. This is where the weld was, and this one had not been weld repaired, and it looks like beautiful. And if you start looking at the things in detail, this was 20% lab-induced sigma phase in that, and sorry for the lousy flare in the middle. You can see the sort of black color here, and then it was heat treated, and you're back to having the ferrite and austenite. So very, very low levels of sigma phase. And that's it. Oh, I just about finished on time. Now, what were the questions?
Yeah, Graham, there are a few questions in the Q&A.
Okay, if three different metals in contact, carbon steel, aluminium, and stainless steel, which one will corrode and why? Well, the why is because the one that is going to be most anodic will corrode. That's not quite so simple though, because it's not only the potential that matters, but also whether it forms stable oxides. So if you put these three together, then the carbon steel will corrode because it's not got any protection at all. The aluminium will corrode less, but it may pit. And the stainless steel, it's basically got a passive film on the surface and it'll sit there. And actually it will drive the corrosion of both the other two. We're not sharing the PowerPoint. We'll share a PDF of the entire presentation. This one didn't get to a question.
We will be sharing this video. All the parts.
Oh, you'll be sharing the video, okay. But we'll also send you a copy of the PDF.
Yeah, right.
Can I use duplex bolts on 317 parts in seawater immersion service? Because the 316 fasteners are corroding fast. I'm not surprised that they're corroding fast. If you're putting 316 into seawater, it's going to be a real problem. And even 317, it really won't help all that much. You look at the pitting resistance equivalent. There's a Nickel Institute publication called, it's 11021, and there's some graphs in there showing what happens if you're putting seawater onto, it's actually looking at crevice corrosion. And not until you get up to the super duplex or the super austenitics do you actually find that you get away from having crevice corrosion. And that's basically what would happen, I think. 316 won't like it, the 317 won't like it, and the duplex, can you use duplex on the 317 part? Yeah. How does the 317 actually go in the seawater? I wouldn't have expected it to be. I suppose if the seawater is cool, it might be reasonable, but even duplex in seawater is not terribly good. Other questions? Oh, goodness, there are lots more. Right. Oh, yes.
Yeah, there are a few more.
Right. Okay. Oh, thank you. Effect on high temperature dissimilar metal welding. It's going to depend on what, I'm not sure what the temperature effect on it's really going to be that there won't be any particular difference. I mean, all the potentials are going to be changed in the same direction by the going up to higher temperatures, and all you're really going to do is put the corrosion rate up if there's going to be corrosion. And the rule of thumb on that is 10 degrees C, you double the corrosion rates. So if you've got, it's a very rough rule of thumb. It's actually about 1.6. If we weld ferritic and austenitic stainless steels, which will corrode first? It will depend. If you're looking at the same PRE, then they would, well, the ferritic actually would be a real problem, because welding ferritics, you need to be very careful to make sure that you don't introduce interstitial material and tend to get cracking and so on, or grain growth. Actually, that's the other problem, you'll get grain growth. Yeah, dissimilar metal. Look, it's a whole new topic. If you're talking about welding of different stainless steels together, or really different materials together, then it's fun and games. Look, ferritics are just difficult to weld. The modern ones, very pure, and you need to have absolutely clean, and you have to have very good gas shielding. Otherwise, you can get all sorts of strife. When we have 316 with alloy 1817 M40, what would happen? Good question. Gary, do you know?
Sorry,
Gary?
I presume 817 M40 is a carbon steel, is it?
Yeah, well, I would imagine so. So,
But I don't know.
Yeah, I think it's a grade of alloy steel.
it's a grade of?
Alloy steel, I think.
Alloy steel, yeah, okay. But still not in corrosion resistance near a stainless
right.
steel. Did a chrome moly type alloy steel, or?
Oh, it doesn't
Anyhow.
look like.
Yeah. I think,
maybe some high strength alloy steel.
Yeah, that starts getting hairy. Just because of the heat treatment that you have to do.
Yeah,
look,
right.
off the top, we'll have a look. I'm sorry, I can't off the top of my head talk. It's just, it's the heat treatment after that's going to be the issue. In duplex stainless steel weldment, is it passive stability or microstructure play the major role in corrosion? Well, the passive stability is basically the surface, and that's a matter of cleaning up the surface afterwards. The microstructure is going to depend on how much heat you put into it, how quickly you cooled it down, and also basically whether you followed your weld procedures in terms of the consumable, in terms of the gas shielding, and so on. So the passive film is easy to fix up, but the microstructure inside it is going to be a problem, or potentially a problem, if it's been heated too much, or if it's been cooled down too fast, or sorry, too slowly usually. Where are we? Can I talk about galvanically induced hydrogen stress cracking? Are the factors that affect galvanic corrosion to play? In this case, a stray current, could that exacerbate the damage? Anytime you get corrosion in an acidic environment, well, slightly acidic, you get some level of hydrogen generated, and depending on whether there are hydrogen poisons around, then instead of the hydrogen coming off, it can diffuse in, and you can wind up with hydrogen stress cracking. There are any number of reasonably recognized ways of dealing with it, but low temperature stuff, you can usually bake things. But it's a matter of making sure that you've got, if you're sensitive to hydrogen cracking, then you make sure that everything is dry, and you actually make sure that, yeah, you just don't basically keep things dry. What happens when titanium and cadmium plated join together? Oh dear. I don't like the sound of that. Gary,
that's a good.
got a thought?
No. Something that has to be investigated. Yeah, as you say, I don't.
Maybe,
my
Gary,
first
you can,
reaction is I
check.
don't like the idea.
You can write. Maybe you can refer and write to me.
It sounds like aerospace stuff where you've got some lots of different systems being done, and yeah, I'm just not sure.
Yeah, maybe you can check back and write to us. We will pass it over to the.
Yeah, okay, all right, we'll see what we can do. Will we get a bundle of the list of this, or can you send it to us?
Yeah, I will send you the list of questions.
Okay, fine. Washers or rubber gaskets are put to insulate and stop galvanic corrosion, but crevice corrosion can still be detrimental. Is it possible in larger degrees? I don't quite understand the way the question is, but I quite agree with you that you put in gaskets or insulation. It's better if your insulation is not too compressible, because as you compress something, the gasket, the crevice gets tighter and tighter, and it's recognized, and there's lots of theoretical and practical stuff showing that it's a problem, even to the extent if you've got a rubber gasket that extends over the edge into a water stream, which you would think would be okay, then at the edge you've got a very, very tight crevice, and you can get crevice corrosion when you would not normally expect it. You're probably better off having a slight step in, millimeter perhaps, where the gasket has been compressed. But it's better, really, if you're talking about high pressure stuff, to have fiber gaskets, which are slightly compressible, but not very much. And desal plants, for instance, they just don't, they don't use rubber. What is PWC? Did I say PWC somewhere? Anybody remember it? Sorry, I don't know. We've got this titanium and cadmium plated steel come together. Yeah, look, I'm not able to answer that at the moment. Carbon steel tube weld overlaid with 347 and adjoining carbon steel channel shell. Will it cause serious corrosion problem? Depends what's there. If the carbon steel overlaid with adjoining carbons, why would you not have, say, overlaid with an adjoining carbon steel channel shell? If there, you would either have.
It's not clear.
Yeah, I mean, there's no problem with the overlay, but it's a matter of protecting the carbon steel. And what the temperature was, I mean, quite commonly, it would just be coated. You could have galvanic protection in there. I'm just not sure of the actual circumstances. How CFC aluminium corrosion happens. I'm sorry, I'm ignorant. What's CFC? Carbon fiber composite to aluminium corrosion happens. Yeah, well, it can and does, because carbon's right up one end and aluminium's right up the other end. So there will be corrosion there. Carbon fiber composite. What's the composite? Is it aluminium? And then you've got the cut ends. Ding, ding, ding. Send me the thing. I'll have a look. CFC and aluminium. Book for corrosion of stainless steels. Well, there's Cedric's. That's an old book. Been around for a long while. Corrosion, it's called Corrosion of Stainless Steels. And there's an enormous amount. Go have a look at the stainless steel doctor, corrosion doctor, I think. There's so much stuff on the web, and provided it's reasonably competent, then it's a good place to start. But I'm not sure exactly what you're looking at, what you actually want. Summer training postdoc in your esteemed organisation. Nicholas Institute doesn't do that. Is it possible?
Graham, I think, I think you have taken almost all the questions. Remaining, we will send it over to you by mail.
Okay, thank you. I'm sorry, I've run a quarter of an hour over time.
Right, so that you can just go through and reply it in a better way. And we will also be sharing this recording to all the participants after uploading this into YouTube. So all of them can refer as and when they request. Yeah. So on behalf of IAW Mumbai branch, we thank you for your valuable time and sharing with us, the more and more details with respect to corrosion, galvanic corrosion. And special thanks to Jörg and Mr. Gary, who has been supporting us all these, almost 2 to 3 years now. So special thanks to Mitchell Institute and also the Stainless Steel Association India. Yeah, so we really looking forward to many such discussions and seminars from both institutes.
Okay.
Yeah, thank you so much. Yeah.
Right.
Well,
Thank you very much.
Guys, yes.
Yeah, thanks, Jörg and Gary.
Okay,
Thank
okay. Have a good rest of the evening.
you. We can.
You all have a good one.
Yeah.
Yeah.
Thank you so much.
Okay, thanks, people.
Okay,
Bye.
bye-bye.
Where are we? Stop sharing. How do I stop sharing? There. Done. Yes. Thanks,
Have a
you.
lovely rest of the weekend. Thank you, Graham.
Rest of the
Nimesh,
weekend. Oh, of course, it's
everybody.
Saturday night, isn't it? Yes.
Yeah,
Hey,
it's Saturday night. Yes,
Have
yes,
you had
yes.
fireworks yet?
No, not yet. It's still quiet. Another
Okay.
3 hours to go, 2.5.
Fair enough. Okay. All right.
All
Thank
the
you.
best. Thanks. Goodbye.
Bye. Where are we? Get rid of that and stop in.